All right. Hello, everybody. Welcome to the Modern Web Podcast. My name is Rob Ocel. I'm a developer at this.labs, and I'm going to be your host today. I'm joined today by my co-host, Jake Dohm, who's a developer at Goodwork. And today we're going to be talking about compilers. Joining us to discuss this is Minko Gechev, who's on the Angular team at Google. We also have Radoslav Kirov, who is on the TypeScript language support team at Google. And we have Kristofer Baxter, who is a self-styled creator of web pages and performance expert trying to make the internet at least 1% faster each year. So that's his formal title. So with that, why don't we get started? And Jake, why don't you get us started with the first question?
Sure thing. So before we jump into talking about all the different compilers and what they do, let's just preface it with what a compiler is. So I'll throw that out there. And Minko, do you want to jump on that question?
Yeah, sure. So basically, the compiler transforms one language to another, one programming language to another. In the that's the most simple definition that we can provide. The target language, it can be on different level. It can be very low language, such as assembly, or it can be a higher language. For example, we have a lot of compilers which produce JavaScript.
Okay.
That's pretty much it.
And how, so I think other people, I know I've heard terms like transpilers, people have heard interpreters. Some people thought that compilers were only about doing C++ or languages like that. So how should web developers and JavaScript developers in particular understand the differences between compilers, interpreters, transpilers, or is there not as much difference as people think?
There are quite a few differences. Well, specifically compiler and transpiler, I'm often using them. Using transpilers when I'm referring to a compiler which produces target language, where the target language is from higher level, for example, JavaScript. Although I'm not confident about the formal definition, if there is one. Usually from the publication that I have read, usually they're referring to everything as a compiler, and the interpreter is something else. It is related to, it uses some of the phases from the compiler, but in general, it doesn't produce any source code. It directly interprets an abstract representation of the program.
Yeah, I think the work of all these terms, they kind of started in computer science, and as they spread their usage, they lose their very formal, strict meaning. So at this point, we have a more colloquial usage, and I think compiler and transpiler in our space, in the web space, I think could be almost interchangeable. And the other thing that there is not a compiler or a transpiler is the interpreter, is the thing that actually executes the program. So as long as it doesn't execute the program and consumes it, we might as well call it a compiler.
Yeah, in fact, I would just stop using the word transpiler entirely. At this point, most of its unique meaning. In fact, I just refer to even something like Babel as just a compiler. It just makes things easier, one less term to try to figure out what it means in a very complicated space.
I think that's what Henry Zhu, the maintainer of Babel, said too at one point. He's like, okay, it might technically be a transpiler, but let's just unify the language and call it a compiler.
Great. So I feel like there has been a lot of movement or at least a lot of heat in the compiler space in web development. A lot of different tools or approaches have popped up. Is there any reason why that's happening now? Why are compilers and tools like these being so big right now? Why are they growing and multiplying?
I think it's very fun to create a compiler, and that's one of the reasons why everyone is creating one. It's also I think everything started in 1995 when JavaScript was developed for 10 days, and this already required us to develop something, a language on top of JavaScript, a language which compiles to JavaScript that solves a lot of the issues which were inherited from the short design, right? So, for example, CoffeeScript, that's why it appeared. It has very simple syntax, very friendly syntax, and it introduces some concepts which were back then when CoffeeScript was trending. We had ECMAScript version 3, so we don't have class syntax, we don't have arrow functions and things like that. And there were a lot of issues around JavaScript. For example, whether we should use triple equal or double equal, things like that. So CoffeeScript was opinionated about these things. And it started the trend with everyone building their own compiler. And since building a compiler is a very fun activity. We have right now maybe hundreds of languages which compile specifically to JavaScript. And
yeah, I'm not aware of a language which does not compile to JavaScript at this point. Whether that's actually used by anybody in production, a lot of them I think are more of a play, theoretical. But yeah.
Awesome. So besides the fun aspect, which I mean, I know people that have worked on these kind of things, and I think we'll talk about this later, but I know people that have worked on Babel plugins that have gotten really into these concepts when they've been investigating that. But what are the actual technical challenges that are trying to be solved by some of these? I mean, I think Babel is one of the ones that people are most familiar with because it kind of lets them use features that maybe aren't generally supported. But there's other ones maybe like Svelte or TypeScript that are kind of have different approaches. So what are the technical things that we're trying to accomplish in this space with some of these different compilers?
I think it all boils down to this gap where the web is the biggest platform, the most ubiquitous platform. That's where all the users are. And then here are the developers, and they have their own. The developers want to write a language that may be different than what the platform gives. And to bridge this gap, you put a compiler in the middle, and the gap disappears, right? Because I can write in language A, output language B. That's what's consumed by the web platform. And now A and B could be anywhere from JavaScript of different versions or very fancy like Haskell or Scala to JavaScript. But the platform is JavaScript. That's the one thing that's in everybody's browser. So
I would actually take it a little bit of a different angle. I think that our applications have just become far more ambitious on the web. And as a result of that, we needed to introduce things like compilers. The first compiler I used in a commercial sense was Dean Edwards Packer. And the benefit there was that as I was able to deliver a lot more functionality without a huge impact to user experience. And so what I've seen in the web industry is this kind of trend towards more complex, powerful applications, and these applications tend to require more compilation technologies.
I'm curious what specifically the compiler provided on top of what the web platform currently does provide for you. I can see some other features that the compilers bring to the web platform. For example, the Angular compiler and the Svelte, for example, they're taking declarative templates and compiling them to more efficient representation, which invokes direct invocation of functions that are going to render the view in the most efficient way. That's from a different angle. So of course we have our own preferences. As Rado said, some of us prefer to write with very strict language, not strict, but functional language with very formal type system like PureScript, let's say, and others prefer. So this is one of the motivations, I guess. The second one is to produce more efficient source code from very declarative and user-friendly syntax, let's say. For example, Angular templates or Svelte. Or Ember as well. Glimmer there is. That's another topic, actually, which we can discuss.
And then another motivation, as Rado mentioned, is compiling back to ES5 or a version of JavaScript that's supported in older browsers. So there's kind of a bunch of different reasons you might want a compiler in between you and the code you write and the code you ship, which is why so many people are using one as opposed to 5-10 years ago when you might minify it, but pretty much the code you write is the code you're going to put on your site. That doesn't happen very often anymore.
Yeah, life was much simpler.
For better or for worse.
I think historically, really, the big explosion happened with ES6, right? Because then it felt, even people who were a little bit on the fence about adding tooling, they were like, well, it's an intermediate state, maybe. Maybe at some point ES5 will become ES6 and we won't need this tool. But of course, though, I feel that was a little bit of a, it didn't pan out like that because now we have ES7 and there's always, I think the spec keeps growing and I think we're never getting the compilers out of our tool chains.
Yeah, Babel was even called 5 to 6 initially, right?
Yeah, right. So
that's an interesting bridge because I wasn't aware of this until before we started the podcast, but we're introduced to the concept of like a Labatt style compiler, so something that's almost kind of working in the opposite direction. So Chris, did you kind of want to introduce that concept and kind of why such a thing would actually be useful?
Yeah, so it's really interesting. The V8 team and other JavaScript teams, teams working on JavaScript interpreters, have spent a lot of energy on making sure that more modern, newer syntax runs efficiently within the browser or within a browser context. A script type module can avoid a whole lot of overhead of compatibility that a regular script tag must make sure to execute correctly. And as a result, there's a whole series of compilers now that are starting to emerge that do Labatt style transforms. So instead of going from ES 2017 down to ES5, it's take your current source and move it up. A good example of this is you have a function that returns a promise. That function might actually be better represented as an async function, given the right conditions.
Sorry, you're saying Labatt like bubbles backwards? Is that
exactly? There's actually.
Okay, I wasn't sure. Okay, that's clever. I
will not take credit for the name. I think it's a fantastic name. But this style of transformation is kind of what we're going to see a lot more in compilers very soon, where you're able to use whole program analysis to figure out you've got an array that you run multiple for eaches over instead of running them all in one specific method. Is that an optimization that makes sense given this? And those are the kind of things that you see in other compilers. So this is the kind of optimizations that you see in GCC with 03 or 05. And these kind of optimizations make programs more efficient without changing the root source code. You combine that with module, no module, or other approaches that will allow for differential bundling and serving. You start to get a way to deliver the more modern code that's really efficient, even on devices that may be low powered, but with a newer JS engine. And you still get to support compatibility-wise those older user agents that may be on really powerful hardware still, but just don't have the capability to run that newer syntax.
So we started out converting our new code to old code, and now we're making sure that the code we write that uses slightly older syntax is the newest and fastest it can be. Kind of a fun thing to watch the compilers kind of flip on there and start doing both even.
I have a question about the transformation. Does it make sense to put it all the way back to the source, or is this just a transformation for the bundle? Because the modernization, like there's also need for, I want to run this, but not to emit a bundle, but to modify my sources to be modern, and then check it into the repo and be done with that.
Yeah, like a code mod for your original root source is another compiler, right?
Yep.
I think it depends on the scenario of what you're trying to achieve. So in some places, the code is more expressive to the authors in the original source format, but can be more optimally delivered through a compiler step. That makes sense in that case. There's other times where changing something from an older syntax to newer syntax just makes sense. And those code mods are a perfect way to execute that, especially on something like a major revision of your framework. That is a great way to gain adherence and compliance across large swaths of code.
And the amazing part is the compiler technology you need to build all of this is pretty much the same. It just depends what you do with it.
Yeah.
Interesting. I mean, I like this concept of, and I hadn't thought about it in this way, but like of compilers, like smart people making compilers that help everybody do something a little bit better. So it's like almost like a developer experience thing in some level, right? Like we're talking about, you might not know exactly the right way to represent your code, but this helps you. Or you may not, you may fall into some issues with typing, so you can, use TypeScript or something like it and have it compile into, a different format that kind of takes those away so it doesn't have a runtime effect. Is that why compiler use is growing, and why is that part of what's making this so good? Is that it's kind of helping everybody be more productive or making the whole web faster without people necessarily having to know why things are getting faster?
Yeah, that's a good point. Yeah, we're getting more productive and the web is getting faster. That's a good point. And there could be also different. Yeah, that's another thing. There could be different periods when you're performing the actual compilation. It can be either ahead of time, so you can do the compilation before you ship your application to the user, or it can be just-in-time compilation as well. So, for example, for example, you may want eventually to ship the source code to the user in the form that you have written it, but as part of the execution, you may want to compile some pieces of it just in the meantime while the rest of the source code is being executed. For example, that's something that we used to do in Angular with the templates. But yeah, I completely agree with your point.
I think like most powerful tools, it depends on how something's being used. So unfortunately, there's been a lot of downsides of compiler usage within web applications as well. I can't tell you how many bundles I look at that have class transformations that are not loose enough and as a result add a lot of boilerplate, or how many copies of object-assigned polyfill exist in a bundle so that way the compiler can assume that it exists in a specific context. So there are downsides as well to compilers and their impact on overall web performance. But in the grand scheme of things, I think compilers are really required to get us to that, the set of functionality and requirements that we have about what we want the web to be, but allow us to do that in a way that doesn't impact performance in the long run. About progressive transpilation, about moving towards the newer syntax and still supporting older users, but maybe they have a slightly slower experience.
Great. And you know, one of the things that I was thinking about is there are a lot of different types of compilers. Like I know, like with the typing systems as one example, there was a lot of conversation about whether to use TypeScript or alternatives recently. And I wondered if this mirrored at all some of the conversations that happened around frameworks. I mean, they still happen, but were really prevalent a few years ago, where people were saying, don't use that, it's slow, or you know, people would joke that there was a new framework every day in JavaScript and things like that. Like, how should people that are really fascinated by what these compilers can do for them, but are worried about putting something in their system that might be doing something either they don't understand, or maybe it's not going to last for a long time, like how should people experiment with, incorporate, and evaluate these different tools on their projects?
So I think they should. The one nice thing about all this tooling for people that are older like me, all of them are open source right now, right? So don't treat them as black boxes. They are a little bit different than the programs you write, but at the end they're programs, right? They take some strings and output some other strings. So always measure, you know, like open that bundle, take a look. If you see a lot of object assigned, file a bug, another tool might come and dedupe it, like, sorry to say that the answer to too much compilers might be add more compilers, but again, don't treat them as black boxes. They seem mystical kind of because there's a log accumulation of compilers have existed since we've been programming. So it feels daunting, but it's actually not. At the end of the day, it's just another program. You can debug it. You can put print statements in it. So demystifying, I think, all this goes a long way. And then now you can measure. Now you can start to understand, and maybe interact with the developers of all this tooling because they're all on GitHub, and I think that's one step.
Yeah, I think the ASTExplorer.net is a really good entry into working on compilers.
I use it every day.
Just paste the thing in and see what the abstract syntax tree is, and write a small transformation and see it change before your eyes. That's really powerful, and it's so fast, the turnaround time, that it kind of is like a gateway drug in a sense. Like you really start to play with it. You want to do more and more and more, and it's quite fun.
Yeah, so does someone want to, because that sounds really interesting, does someone want to talk about what an AST is, why it's created, and which compilers use it? Do all compilers use it? Or I know Babel uses it. But if someone wants to talk about that, I'd love to learn more.
Yeah, so it might be a little bit complicated for a user who is new to all of this to just quickly look at the ASTExplorer and completely, well, it's like it provides only limited information. It provides some structural representation of the program in the source code. So in general, the source code first is going to go of the program it is just a string in general. We're just writing strings all day long. That's what we do. And after that, the source code goes through a process of lexical analysis. So basically, each string is basically the program from this string, we're getting a list of substrings. For example, we have an if statement, we have the if keyword, and we have an open parenthesis, and so on and so forth. And as next step, the compiler, the front end of the compiler, is going to produce this tree, abstract syntax tree. This is what AST stands for. So this is going to be produced by taking this list of tokens from the lexical analysis and also getting the grammar of the language, which is just a bunch of rules how we can construct our programs. And from there, we are just generating this abstract syntax tree that we can explore in the AST Explorer. And there are different plugins with different compilers with different plugin models. For example, I haven't used I haven't written Babel plugin, I guess, but from the source plugins that I have read, you're just receiving the AST. You can perform whatever transformations you want to, and you're passing it to the next plugin in the chain. So you can do cool things this way.
One thing to mention is, might be a surprise to people who are new to this. We write one language, but there are many different ASTs, right? Because AST is kind of the internal data representation of the compiler. And if you go to AST Explorer, there's a big dropdown with 10 different options. And at first, that feels like, why it's the same language. But actually, when you get into compiler performance, different compilers have kind of different goals, what they want to do. And ultimately, if you want to optimize those the transformations you do, you have to lay out your data structure in a way that's most efficient for the thing you want to do. And that's why I think the different compilers have different ASTs. If you squint, they all represent the same program, but they might have different names of nodes and so on. And vaguely, they all mirror the ECMAScript spec, right? So if we have notion of class, that class is represented in AST as some kind of node. But there are many variations you can do even beyond that.
And is it usually always a one-step process, or like take the example of TypeScript, because it's a superset of JavaScript. So is there like a stage where it's compiling away the TypeScript internals, and then maybe it's allowing people to do additional transformations, or is that not the right way of thinking about it? Like, is there anything different? I mean, like, because Babel, I understand, is turning one version of JavaScript into another, so that's almost like same to same. But when you go from something either greatly different or from a superset down, does that change at all, the process by which this happens?
So I can speak about TypeScript because that's what I deal with day to day. So it's basically the same. Like if you squint, it's the same pipeline. Right? You take some strings in, you transform it to a big data structure, then you do some transformations on this data structure. The extra part is the types, right? So types are not spec'd by the ECMAScript. So they are after the colon, something comes. That thing needs its own parser, and it's actually quite complicated. It's not just string or number. It could be some fancy stuff like map types, or TypeScript has a very rich type system. And now there's extra step that TypeScript does, which is, okay, I understood these types, but I need to check them, right? So there's this extra step that just goes through this, and its only job is to reject your code. And if it succeeds, it proceeds with the regular transformations that Babel does. And that's why I think recently there's been work to make Babel not check the types of TypeScript, but understand them enough to strip them out and do its transformations. So it can kind of consume TypeScript in the most naive way, which is consume TypeScript, but don't check, just transform. So TypeScript is just a checker plus a transformer, and then it fits into the general framework. Does that make sense?
Yeah, definitely. I mean, while we're kind of talking about these internals, we talked about the AST. Are there any other sort of, for people that might sort of, this has tickled their fancy, so they know the AST Explorer now, are there any other sort of big players in this process of compilation at that super high level that maybe would be useful to kind of introduce, so that when they're reading stuff, that it makes more sense to them, or that kind of explains more of the pipeline of what's sort of happening when something's getting transformed?
Yeah, Rado already mentioned type checking. That's a very well, you don't have this in all compilers, of course, and some compilers they don't have, like, you have either runtime type checking or compile time type checking, or you just run the program and hope it works, and you get some like runtime errors. There is also, well, once you go through all these steps, lexical analysis, syntax analysis, you get the AST, you do the type checking in terms of TypeScript. You also emit some source code, or you can either evaluate the AST. That's where the difference between interpreter and a compiler comes. What you're going to do with this AST? Are you going to generate some source code out of it, or are you going to just interpret it? Or if you want to do something in the middle, you can even analyze this AST and produce some additional warnings, which is basically a linter. The linter is going to go through this AST, provide some analysis on top of it, and give you suggestions on how you should use the language the right way according to some predefined principles. That's it.
So in terms of other popular compilers that people are probably are using or have used and don't realize it, I mean, Webpack is a compiler in many ways, shapes, and forms. So Flow is another popular typed variant of JavaScript that many people use. And there's also things that will compile other types of languages in the web development ecosystem, like CSS compilers. There's plenty of other players in this space. It's really, really large. It's not a very small group of people working on it in the grand scheme of things.
If we're listing, I'll have to add the one I have to interact with daily, which is the Clojure compiler. Clojure with a S. It's a Google JavaScript to JavaScript compiler. Very similar kind of to TypeScript, and that's a big part of my job is creating the tools that allow us to interact between those two tools. The one thing that Clojure is kind of from the get-go optimized for is creating a very small bundle. That's something that the TypeScript doesn't do. So.
And T-SQL.
Optimizing compiler.
T-SQL is amazing. Comes from the Angular team. It definitely needs to be mentioned. It helps you use TypeScript code with Clojure compiler much easier.
One comment about Webpack. I'll prefer to put it into a slightly different category, although in the end it compiles a bunch of assets and produces some efficient output. It is either, it's currently growing into a build system mostly, which has slightly bigger scope because, just to comment on the side, whether it's a bundler or a compiler or a build system.
Yeah, Webpack does it all, but in the classical, like the build system is something that orchestrates the compiler, tells the compiler you run when, and that's actually a non-trivial problem to know a single file change on a disk, what should run, just what should run, right? And what is usually a compiler. So usually the build system calls into the compilers, and Webpack kind of does everything in process, so you cannot easily separate all the pieces. But
yeah, I think three compilers to really, if you want to look at some of the more modern compilers in the web space, I think the Angular compiler that works on the new template syntax with Ivy is fantastic. It's a really good resource. The work being done by Rich Harris on Svelte, it's almost now a custom language that's being written within Svelte templates in Svelte version 3. And the work that the LinkedIn folks are doing on Glimmer is also pretty interesting and very unique. It avoids a lot of the JavaScript overhead.
Yeah, Glimmer, it's fantastic. So it's a compiler which compiles your templates to bytecode, and so it doesn't compile the templates to something which is executable by the browser the way that the Angular compiler, NGTSC, or the Svelte compiler does it. They're compiling something to just a blob, which is just like a combination of instructions. That after that, an interpreter comes in and starts interpreting this blob, this like sequence of instructions. So they're shipping a virtual machine as well. And the reasoning behind this is that if you compile your templates to JavaScript, this means that they need to be parsed. So the JavaScript virtual machine needs to go through lexical analysis and syntax analysis. And because the grammar of JavaScript is very complicated, this is a slow process. So that's why they prefer to ship just one sequence of instructions, which is going to be with their custom parser, which is going to be much faster, which is going to parse this sequence of instructions much faster compared to the way that the JavaScript virtual machine is going to parse a bunch of JavaScript. that's kind of very meta. I like their idea. I don't, and it seems that it's working well in LinkedIn.
Awesome. You know, I know that I don't believe anybody here is an expert or is working on this specifically, but one of the things I think we'd be remiss to at least just mention, even if none of us can talk about it in great depth, is all of the work that's happening with the WebAssembly piece. And I don't know if anybody here is familiar enough with it that they can at least explain any similarities or differences with some of the compilers that we've already talked about, just because I know that's probably a term that a lot of people at least have heard, and they might be curious how that fits into this compiler space. Does anybody know it enough to explain any of the differences?
So it's somewhat similar to what Minko mentioned about. Basically, going back to the definition of compiler, it takes source language to output. We now have a new output, which is WebAssembly, right? So that's the new thing. That is, so initially I said JavaScript's ubiquitous, so most of these compilers output JavaScript because that's what runs in browsers. Well, now we have a second thing that is very, very different from JavaScript. In fact, couldn't be any more different. It's assembly. It's like a very low level. JavaScript is very kind of high level. It doesn't deal with memory allocation. You just say let X, and memory appears, and it disappears whenever. So WebAssembly has to deal with. It's like closer to how your CPU works. So you have to deal with concerns that are very different than the concerns of JavaScript. So it's a new output, and now there's a little bit of a kind of a gold rush to take. All the inputs are very, very various, right? The inputs are thousands. The outputs used to be just JavaScript. Now we have JavaScript and WebAssembly. So there's I think it's like a gold rush to get any language to output WebAssembly. And some languages are better suited to output WebAssembly, and some are less. And ironically, I think JavaScript's not very well suited to output WebAssembly because it's very high-level language. And something like Rust, for example, that is a systems programming language that doesn't have garbage collection is better suited to output WebAssembly. And I've only seen demos with this. I haven't experimented with it myself, but it appears to be working, and they have a WebAssembly output.
I think a nice way to try WebAssembly is something like AssemblyScript. It's very simple and familiar to people who write TypeScript. It's not a highly variant language. It's not highly variant from the TypeScript language itself. And it gets you a lot of the benefits of WASM compilation.
Great. So another topic that was brought up somewhat recently, and I think it's been a conversation for a while, and probably in the compiler space, a well-known problem, but there was a lot of talk about with the web, like people having the ability to view source, right? And so I guess just that concept of whenever you have sidestepping that conversation, but just this idea that compilers output something which is optimized in some way, right? Or just different than what went into it. And so some people might wonder, both to validate what the compiler actually did, but also to maybe understand what was there before the compiler had it. There's these conversations about being able to sort of reverse engineer the process or have some mappings that go back to the original source. Can you guys kind of introduce what that kind of concept is and kind of how some of the compilers might approach that?
Yeah, Mozilla did that a couple of years ago, like 5-10 years, I don't know, 5-10 years ago with the source maps, specifically for JavaScript.
There was a collaboration with the Google Closure compiler folks for all the optimizing compilers.
Yeah, well, basically, together with the generation of the targets program, the compiler is also generating a bunch of metadata, which allows you to map the produced outputs to the original input of the program. So basically, you can run your compiled output in the browser, but debug what you have written originally, because this metadata, together with Chrome DevTools, can produce your original program. That's pretty much what source maps are.
So I think there's one step further that some folks have been struggling with on the web recently. So a good example is the Twitter Lite application, which uses something kind of similar to CSS modules, but it's baked into the React Native Web Framework, and it has its own custom set of syntax for class names. Those names change per build, and they're based on a set of heuristics that you can't really know ahead of time unless you're working within that system. And as a result, it's hard to just scrape their content, for instance, or to modify the look and feel just with CSS alone. You have to be more deeply ingrained in their system to modify the look and feel of the application. I really think there's a hard tipping point between what is an application and what is a website. And something that is more just read-only or has minimal interactions, I would love to make sure that people who are developing those that are using compilers are also producing output that is consumable by others, even if it's not the default output. So you go to index.html and you get something that is compiled, but there's a way to opt into seeing the uncompiled version, for instance, for those kind of sites. This is also really beneficial for things like cataloging our content. It's really important as a society that we have a library of the things that we've built, so we learn not to repeat our mistakes. If we don't make that source indexable or understandable by humans, it's hard for us to go back and look at those things retroactively. So while source maps get us part of the way, I think there are additional things that we as an industry need to figure out how to do better on. How do we maintain the kind of the ethos of, I can just open my the app that I was using and make changes and actually understand what's going on without having to know the entire build process. Is that a worthy goal still, or is there a different way of expressing that kind of demand? I think there's more that we need to do, is really what I'm coming down to. And I think as a result of not having this today, you're seeing frustration from people who want to access the web in a slightly different way.
There was discussion about this recently on Twitter, actually, with DHH from Rails, who was feeling very nostalgic that he no longer can look at the source code and figure out how the application works. I think there is a very interesting, well, we should, yeah, so there are some kind of orthogonal goals here, because in order to ship the application in its original form, we need to also provide some metadata in order to be able to transform it to how it how it looked before all these different transformations, such as like source code modification and compilation and so on and so forth. So it's, yeah, very interesting competing goals there that it's hard to figure out where exactly the balance is.
Yeah, I mean, it's interesting, right? Because I mean, most of the time when you're talking about compilers, or at least traditional compilers, you're thinking about taking something that you wrote with these, with our language glyphs, right, and turning it into assembly that a computer, that a CPU is supposed to understand. So this is one of those weird cases where we are simultaneously compiling something that both a machine and a human potentially could read. I think the conversation is definitely interesting as to, that's an interesting concern.
Yeah, I think the access point that Kristofer mentioned is very important. It's just the question is, do you access it kind of in situ, like right as you're executing? Do you want to access it, or you access it through some indirection? Because again, the primary goal is of the page is to load. Like, most people are not going to do that, and then some people will. And can we get the performance we need for everybody somehow work well with the access that we would like to give to some? And can this be done in an unobtrusive way, right? Can we have it both ways? Which it's hard, but it would be nice to.
And in some cases, that's actually not what we want. Is when we ship the application, we want some fields, for example, to be renamed. We don't want to expose their original names to the end user.
They're busy. Yeah, they're like actual. So I know Google, like lots of products are experimented with, and there's a whole industry that likes, especially on Android, to reverse engineer binaries and try to figure out new product launches and their names. And there's another industry that tries to hide them on the other side, and at some point it feels lots of wasted cycles. So it's a big topic to how to balance those two desires.
Great. I mean, I hope this doesn't introduce a topic that's too large, but this just made me think, when we're talking about being able to trace back what a compiler actually did, what its effects were, so that we can understand it and whether it's working efficiently. I feel like I've heard instances where machine learning has started to be introduced in the concept of compilers to sort of intelligently or to learn how to new ways to combine the code. Does that introduce any complexities in this topic where, it has to output maybe the data that it used to make its decision in addition to the source maps or something in order to kind of help with that process?
Yeah, it's a great topic, because machine learning is, like, obviously in all the other fields is very hot and very widely used at this point. There are lots of papers and academic research being done on, like, using machine learning for on top of compiler technology. Like, let's say here's AST, simple things like, let's say, can you say this AST is similar to this other AST using machine learning model and so on. In practice, though, I have not seen any of that be used in the industry in a serious way, right? So I think it's early days compared to the kind of recommendation system problems that are, machine learning is, or like image recognition, things that machine learning is just dominating. I have not seen in the compiler technology any serious use of machine learning yet, but time will tell.
Yeah, for compile time optimization, I have seen some experiments, but yeah, haven't used anything in practice.
Yeah, same here. I think there is an opportunity for something that's a bit more probabilistic. So it's able to say, I'm going to try 4 or 5 different variants on this different import source and see what the most optimal output is given these conditions, and learn over time how to write an optimizing compiler based off of all of the code you've ever fed me. But it sounds really cool, and I just don't think it's real.
It's like it's almost like the curse of the AST is so structured. Machine learning is really shining in, like, image recognition, where there's just there could be a house behind this car. Like, it's so unstructured. We invent languages because this is invented by us, right? Ultimately, it's not the real world. So the AST has so much structure that the machine learning doesn't shine as much, because it's very good at figuring out the structure. But we know the structure already. So that's why I think it's a harder problem, and it's a still kind of research topic. But I'm sure something will come out in the next 5-10 years.
Well, awesome. Thank you, everybody. That'll do it for today. I want to thank our guests, Minko, who you can find on Twitter at MGECHEV. Also like to thank Rado. Thank you so much for being here. You can find him on Twitter at Radokirov. That's RADOKIROV. And Chris, you can find on Twitter at Kristofer Baxter. So that's KRISTOFERBAXTER. I'd also like to thank my co-host Jake, who you can find on Twitter at Jake Dohm. That's JAKEDOHM. My name is Ocel, and you can find me on Twitter at Robocell. So it's ROBOCELL. To all of you, thanks for listening to the Modern Web Podcast. You can find us online at moderndotweb.com or on Twitter at modern.web. So that's MODERNDOTWEB. All right. Thanks, everybody. Thanks for being here.
Thank you.